Okay, in this section, I'm going to talk about the properties of the definite integral. First, I want to talk about a few that I am not going to discuss in any detail. I just want to list them. So we have this integral from a to b of some constant c dx, and that is just going to be c times b minus a. I'm not going to discuss these because we investigated these in the lab that we did, so you should be able to verify these results in the lab. Another one is the integral from a to a of any function f is going to be 0, right? And that's because basically we have no area here, right? We're not going anywhere. It's just a line at a. And then we have the integral from 0 to b of x dx, and that's just going to be 1/2 b squared. And one way to think of that is that we just have a triangle. So this is just the formula for the area of a triangle, 1/2 base times height, but in this case, base and height are the same, so we end up with b squared. And then finally, integral from a to b of f of x dx plus the integral from b to c of f of x dx is just the integral from a to c of f of x dx. And what this is saying is if we take the area under the curve f from a to b, and then the area from b to c, that's the same as just going from a to c. The areas will be the same. All right. While I'm not going to derive them or verify them, I want to list them because I'll use them as I discuss the other properties of the definite integral. Okay, so the first one I want to talk about is the integral from a to b of f of x plus g of x is the integral from a to b of f of x dx plus the integral from a to b of g of x dx. So I'm going to verify these, I'm not going to prove them. Ultimately, if we think about this as area, it makes sense, right? If we take this function plus this function and we find the area under that curve from a to b, then it makes sense that the area under the sum is just the sum of the two areas separately. Let me just give you a quick example. So if we take the integral from 0 to 3 of x plus 5, all right, so we can think of x as our f and the function y equals 5 as our g, then that is the same as 0 to 3 of x dx plus 0 to 3 of 5 dx. Now I'm going to use my properties up here. So for the first one, I use this property here. So 3 is my b. So this is going to be 1/2 3 times 3 squared. All right, and for this one, I use the first property, right? This is just a rectangle, right? Because c is a constant. So this is going to be plus 5 times 3 minus 0. This is 4.5, half of 9, plus 5 times 3, which is 15. So that's 19.5. Graphically, well, I guess I'll just leave this in the middle here. Graphically, what's going on, we could say, let's take a look at x plus 5. So let's say if this is, here's x plus 5, and we go out to 3. All right, so I have to extend this up a little bit. X plus 5 is going to look something like this. Of course, it keeps going back this way, but we just care about this area right here, right? If this is 3. So what we're saying is that area is 19.5, but that represents this. So I want to show you graphically that it's the same as this. So let's look at let's go out to 3, and so the function just y equals x looks something like that, and we have this area here. So this part, I'll just label it as represented by 0 to 3 of x plus 5 dx, because this function right here is x plus 5. This right here represents 0 to 3 of x dx, because this is just y equals x, this line. And then the other piece is, of course, is that we have just y equals 5. So we're up here, like at 5. This is y equals 5. We come out to 3, and we have found this area here, right? So notice that basically what we've done is we've taken this area here and we divided this top part right here is the same as this, and this bottom part is what we have going on right here. Okay, so much for that one. A couple of other properties. We have the integral from a to b of a constant times function is the same thing as the constant times the integral. All right. So if we take a constant times a function, the area under that curve from a to b is the same thing as the area under the curve times the constant. So a quick example of that, if we go from 0 to 3 of 2x dx, well, that's the same as 2 times the integral from 0 to 3 of x dx. Again, using the same property we did before, so this is 2 times, that's going to be 1/2 times 3 squared. Well, 2 times 1/2 is just 1, so that just gives us 9. Graphically, what we have going on, if we do 2x, right, so we could say we're up 2 over 1, so our graph here would look something like this. This is 2x, and if we go out to 3, then that area is 9, all right? Whereas if we just look at y equals x, all right, we go out to 3, that area is half. So again, if you think about this being a triangle, 1/2 base times height, right? But the side of this is twice as long as the side of this, so that makes sense that if we take the double of this, we get this area. I mean, this is a special case in terms of a linear function, so we're dealing with triangles, but I want to point out this is true for any function. We can take that constant out front, find the area under that curve from a to b, and then multiply by the constant. Okay, what are some other ones? We have the integral from a to b, f of x dx, equals negative of the integral from b to a of f of x dx. And I think probably the easiest way to see this is we think about when we take the areas here, we are basically taking the limit as n goes to infinity, and we're summing from I equals 1 to n of f of x sub I times delta x, where this is the height of our rectangle, this is the width of our rectangle. We're taking the limit as n goes to infinity. So if you think about these in terms of rectangles, then what is delta x? Well, delta x is b minus a over n, right? This is the case where all of our rectangles have the same width. So we just take the length of our interval, b minus a, and we divide it by n. That gives us the width. But notice that that is the negative of a minus b over n, right? If I distribute that negative, I end up with b minus a. So when we switch, when we go from b to a, instead of from a to b, then we're essentially going the other direction. We're going so that we end up with kind of a negative width to our rectangle. So the area will be the same, except it'll be negative because we're going the other direction. That's basically all that says. All right, so just a couple more here. If f of x is less than or equal to g of x for all x in some closed interval a, b, then the integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. So, and this also makes sense graphically, right? We can kind of, let's just real quick I'm going to draw something. I'll get a couple other colors out here. So let's say that something like this is our f of x. And then, I don't know, maybe a green one. So we have something like this for g of x. All right? And let's say here's a and here is b. So we kind of go up here. All right, so notice that between a and b, f is always less than g. All right, so all this says is if one function is always greater than the other, then this area down here underneath f will always be less than the area underneath g. So that intuitively, that makes a lot of sense. I want to caution you, however, that the converse is not true. And what do I mean by the converse? So, suppose the integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. Does that mean, and I mean this always, does it mean always that f of x is less than or equal to g of x for all x in a, b? Question mark. All right. So if the area under f is less than or equal to the area under g between a and b, does that mean the one function is always less than the other? The answer is no. So let me just give you a quick example. So let's look at the area. Let's look at the integral from 0 to 6 of 2 dx. Well, we know from our first property that that's 2 times 6 minus 0, which is 12. All right, and then we can look at also from 0 to 6 of x minus 3 dx. All right, we can separate that out. 0 to 6 of x dx minus 0 to 6 of 3 dx. All right, so this one is going to be 1/2 6 squared minus 3 times 6 minus 0. Well, 1/2 of 36 is 18, minus 3 times 6 is 18. So that's 0. So clearly, this is less than that, right? So we have the 0 to 6 of x minus 3 dx is less than 0 to 6 of 2 dx. So does that imply that x minus 3 is always less than 2? Well, if we look at the graph, that's clearly not the case. All right, so if we go down to -3 up to +3, we cross at 3, and here's our 6. So this is x minus 3, right? And what we end up happening here is we have this area here, this area here. This area is negative, this area is positive, but they're the same. So the total area is 0. I haven't drawn this symmetrically, but you get the idea. Whereas y equals 2, I'll use another color for this, would come across here like this. And so that area here is 12. All right? But notice that along that interval, yes, from out here to the point where they intersect, which should be 5, this is y equals 2 is greater than x minus 3. But out here, it's not. All right? So it's not true that x minus 3 is always less than 2x, because x minus 3 is greater than 2x along here. So it's primarily because you can have this canceling out. If your function goes below the x-axis, we get this negative area. And so you can have this canceling out with the areas. So it doesn't necessarily imply that one function, if the area is less than, it doesn't necessarily mean that the function is less than. But up here, what this is saying is if one function is always greater than the other function, then it will be true of the areas as well. And that's what this example is here. All right, so that's what I have for properties of the definite integral.